Suderman, and we're now going to look at a video of Chapter 1, Section 6, Relations and Functions. Okay, first of all, let's warm up looking at this problem right here. Using this graph, list the x-coordinates of the points. Okay, so we have 4 points, and our x-coordinates are -2, 0, 3, and 5. It's always good to list them from smallest to biggest. Now let's list the y-coordinates of these points. So our smallest y-coordinate is 0. Then we have 1 at 1. Then we have 1, 2, 3. Then we've got 4. Okay. So relation is a pairing of input values with output values. It can be shown as a set of ordered pairs x and y, where x is an input and y is an output. The set of input values for a relation is called the domain, and the set of output values is called the range. So let's look at a mapping diagram. So here we have 2, and that's our set, and we're going to call that domain. And our range is going to be A, B, and C. So if we decide that if 2 is our input value and its output value is A, also an output value is B, and also an output value of C, in other words, we've just related the items in our domain to the items in our range. And here's our ordered pairs. Then this is a relation, because we have now paired 2 with A, 2 with B, and 2 with C, which is shown in our ordered pairs. And 2 is our input, and A, B, and C are our output. Therefore, 2 is our domain, and our range consists of A, B, and C. So let's look at an example. Give the domain and range for this relation. So we're given this list of ordered pairs. So if we were to list out the set of ordered pairs, give the domain and range, let's do just that. So the set of ordered pairs, well, it's given to us as ordered pairs, so that's exactly what we'll write. So 105, 125, 146, 160, 160, 6, and 180, 12. Okay, so remember that the domain will be all of our input values, in other words, all of x values. So it'd be the first item in each of those set of parentheses in the ordered pairs. So our domain is going to be 100, 120, 140, 160, and 180. And our range will be the y values of each of our ordered pairs. Okay, so our range would be 5, 6, and 12. Notice I did not write the repeated ones. I didn't repeat them in my range. Even though 5 occurred twice, I only need to note it once. So let's look at the domain range for the relation shown in this graph. So let's start out the same way. Let's list the set of ordered pairs. Okay, so we've got -2, 2. Well, whoops, let me fix this. There we go. -1, 1, 0, 0, 1, -1, 2, -2, and finally 3, -3. And these little braces here, these curly looking lines, that's just to say that this is a set. So there's a set, and on the inside is all of our ordered pairs. Okay, next part, the domain. So again, the domain is the x values. So our domain will be from smallest to biggest to -2, -1, 0, 1, 2, and 3. And our range is all of the y values. So again, smallest to biggest, -3, -2, -1, 0, 1, 2. Okay, so you'll notice the way that we write the domain and range. So far we've been looking at it as roster notation. You've heard a teacher say sometimes that they need to check the class roster, or the roster is a list of all the names of students in a class. Well, it is what it sounds like. Roster notation would be listing things out, whereas interval is saying we can include all of the values between these two numbers. So let's look at this. First, let's check out roster. So I'm going to write this in blue. If we are given these points here, the domain will be the set of all the x values. So we get -2, 0, 3, and 5. And the range will be all of the y values. So we have smallest to biggest 0, 1, 3, and 4. Okay, now to check out interval notation, I'm going to do something a little different here. I'm going to connect these points, because I want to include not just those points, but all of the points in between as well. And so if I wanted to connect them and look at it in interval notation, I would write it like this. So I want to include all of the x values from -2 to 5. So I'll say -2 is less than or equal to x is less than or equal to 5. And I'm saying it's less than or equal to because these points on the end are colored in, so we're including them, but we're saying all of the x values between -2 and 5. The range is very similar, except instead of using an x, we'll use y, and we say what's our smallest y value? It's 0. So 0 is less than or equal to y is less than or equal to, and what's our biggest y value? 4. So be careful not to just pick that last point just because it's all the way over there. Okay, so we know what a relation is. It's pairing input values with output values. But what is a function? Well, let's define a function. A function is a relation where every input value is paired with exactly one output value. Okay? So let's take a look at these two. Which of these mapping diagrams represents a function if a function is pairing an input value with exactly one output value? If you picked the top item, then you are incorrect. That is not a function, because our input value of 2 is paired with 3 output values. However, if you picked the mapping diagram on the bottom, then you are correct, because each input value is only paired with exactly one output value. So even though these two things look really similar, one of them is just a relation on the top, but it is not a function. The bottom is still a relation, but it's also a function. So let's check this out. Determine whether each relation is a function. So we have shoe prices. So we have sizes of shoes, 7, 8, and 9. And the prices are 35, 35, and 35. Is this a relation or a function? Oops. As it turns out, this is a function because each input value only has one output value. So yes, it is. And how about B? From the number of items in a grocery cart to the total cost of the items in the cart. So if we bought, say we bought 6 expensive items and it cost us $100. But say we bought 6 cheap items and it only cost us $5. Well, our input value is still the same. So instead of looking at this as 2 separate relationships here, we'll say 6 is related to 100, but 6 is also related to 5. So this is not a function. Okay. Every point on a vertical line has the same x-coordinate, so a vertical line cannot represent a function. If a vertical line passes through more than one point on the graph of a relation, the relation must have more than one point with the same x-coordinate. Therefore, the relation is not a function. A lot of words, right? It's easier to look at it in a picture. So say we have this graph, excuse me, with this vertical line seen in pink. Or we could have this over here, this sideways looking parabola. That line you see moving across the screen is representing the vertical line test. So if we take a vertical line and drag it across our graph, does it ever hit the graph at more than one point? Yes, it does. Therefore, it's not a function. So here's what it looks like in your textbook. It gives us 2 different examples. So here we have this squiggly looking graph, and we've got these dotted lines are the vertical line. Well, no matter where we place the vertical line, it only crosses the graph in exactly one point. Whereas over here on the other side, we have this sideways function here, or relation. It crosses this vertical line in 2 spots. And since it hits the graph more than once, it is not a function. Okay, so let's use a vertical line test to determine whether this relation is a function. And if not, identify 2 points a vertical line would pass through. So what do you think? Is it a relation? Is this relation a function? How about now? The vertical line moving across the graph never hits the graph in more than one point. Therefore, this is a function. Let's look at the same thing on this graph. Is this relation a function? Do you agree with your original thought? Now that you see the line moving across the graph? Well, you'll notice that it's always hitting 2 points at the same time. So this is not a function. So we need to identify 2 points that a vertical line, 2 points that a vertical line would pass through. We have 1, 1, and 1, negative 2. We could have negative 2, 3, and negative 2, 0. We could have 4, negative 1, and 4, negative 4, and more. Those were just a few examples. And finally, let's look at this one. Is this relation a function? Use this line to help you confirm your answer. It is not a function. Well, why not? You'll notice right here that the line crosses these 2 points at the exact same time. So even though there's a break, it still hits 2 points at the same time on the vertical line. Therefore, this is not a function. Okay, well that's it. I hope this helps, and I'll see you tomorrow, and we'll be discussing discrete and continuous. Bye!